Alright, so what we're going to do in this video is talk about a geometric intuition or interpretation for inner products and complex inner products. So we'll start we'll start pretty easy. So we'll start with a one-dimensional vector. So just like a one-dimensional vector is just a scalar. So if you have just A, dot B, right? That's the same as just A1 times B1, right? So, well, I know this is really simple, but it's an important place to start. So let's just do an example. So let's say A1 is like 5, and then B1 is 2, right? So now one way to draw that is so 5, 1, 2, 3, 4, 5 right here, and then so that's A, which is also just A1, right? And then B is 2, so it's right here. So B is B1, right? So this multiplication, another way to think about that is if you rotate one of them up, then it would be the square inside them. So I'm just going to rotate A. So up by 5, so that's A, and then this is B, and so now this area inside here, this is 10, right? And that's the value of this dot product. So that's one way to think about it. So if you rotate your first vector or your first thing by 90, and then you draw this square in here, that's going to be your area. And then there's one other little step you can do is you can squish it such that one of the dimensions is just 1, so that way the whole other thing. So if this is 10, this is the same thing as just having 1 here and then going 10 over. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This box here also has an area of 10. So these are the same. And I only show this part because it's going to be helpful later, right? So this is step 1. So step 2 is we're going to make these complex vectors, but we're going to keep them one-dimensional. So let's again do A dot B, right? And actually dot is probably the wrong notation, so maybe just calling it like an inner product is more correct if they're complex. So what this is now we have, well, so the complex inner product is, so it's A1 plus A2I, and then B1 plus B2I, right? It's this inner product here. And so if you're one-dimensional and you have a complex inner product, this is just, A times B conjugate, right? So the same thing here, I'm going to just make this a negative sign, and then then we can just do multiplication, right? So it's A1 plus A2I times B1 minus B2I, right? So I'm taking this conjugate here. And so you can do the foiling, and there's actually a couple cool things that happen. So the first one is on our real component, it's A1 times B1, A1 B1, and then minus A2 times B2, but then we also have I squared, so that becomes plus A2 B2. And that actually, so this is the real component. This is actually the normal dot product, right? So if you pretend that these were real numbers, this would be gone. Like if this, so you can draw the complex vectors, the complex scalars, like, right? So you can draw one here and another one here, right? So if this is A1, this is A2, this is B1, this is B2, if you took the dot product of those two, it would be A1 times B1 plus A2 B2. And that's exactly what this is here. So it's almost like the real component is just as if you would have pretended they were normal two-dimensional vectors. All right, so let's get back to it. So this is the real component, and now the imaginary component is going to be I times, so it's this A2 B1, and then minus A1 B2. That's a 1. Minus A1 B2. And this term right here, this is actually the cross product. Again, if we view them like this, it's telling you the perpendicular component, and then this one is telling you how much they go together. So that's sort of, that's kind of the cool intuition, but we're going to come back to this real quick. So what we do is we have two vectors. You can treat them as vectors, but really they're just scalars, right? They're just two complex numbers. So one is going to be here, right? So let's call this A, and then B is going to be right here, B. So our intuition is you rotate A by 90 degrees, and then you see how much it goes in the same direction. I'm going to pause here, and then we'll get back to it in the next video.